The Moon 3.5 billion years ago had some large differences to the way it is now, but from a distance it was still recognizably the same object it is today. Probably the most important difference is that it likely had an atmosphere. A 2017 study estimated the composition in the atmospheric pressure that was present through the rock samples brought back to Earth during the Apollo missions. Besides the rock samples, these mare areas, the dark spots on the Moon, also have basalt units, which is solidified lava. Those units were then used to estimate the amount of erupted lava, and both the rock and these units then provided an estimate of the total mass of the gases released, along with the composition. The conclusion from the study is that the Moon 3.5 billion years ago, through the gases released from the volcanic activity, accumulated an atmosphere that had a pressure about 1% of Earth's current atmospheric pressure. That may sound low, and in a way it is, but that is still about 1.5 times the atmospheric pressure that Mars has currently. And Mars still has a visible atmosphere with weather patterns. So what the Moon had back then certainly wasn't insignificant. It was very likely visible from space, and even from Earth, that atmosphere gave the Moon likely a different look. During the night, the Moon's atmosphere had a height between 10 and 30 kilometers. However, during the day, when the temperature dramatically increased, then its height also dramatically increased as well. During the day, it was between 60 and 100 kilometers. The weak surface gravity, in combination with drastic temperature differences between day and night, is what caused for such a significant contraction and expansion of the atmosphere between the day and night. Through assessing rock samples, the composition of the gases released during the eruptions was gathered, and the results are that the most prevalent gas was carbon monoxide, then sulfur, and then water vapor. The authors estimate that the water vapor released from the interior into the atmosphere also made its way to the poles. It's fairly obvious that it could do this as a component of the atmosphere. However, they also suggest that part of that water vapor then got frozen in the permanently shadowed regions, so polar craters. The authors estimate that only 0.1% of the vented water would need to get trapped, as in get frozen, in the permanently shadowed regions to account for all of that water ice present at those locations now. Some studies suggest that the water ice present there is ancient, so it really could be from it being in the atmosphere 3.5 billion years ago. This then means that the water came from internal sources and not from the outside. However, this isn't entirely known, and it could be a combination of both. 3.5 billion years ago, the Moon's distance to Earth was 300,000 kilometers instead of the current 380,000 kilometers. This closer distance certainly made the Moon appear to be slightly larger in the sky. Given the same transparency, then the Moon's atmosphere would likely be visible. The Moon, because of the closer distance, needed about 20 days to complete an orbit around Earth instead of 27 days that it needs now. This graph gives an overview of the total amount of erupted basalt over time. Clearly, 3.5 billion years ago is when volcanic activity peaked. After that time point, volcanic activity is comparatively dead. These intense eruptions are also what allowed for the atmosphere to form. Interestingly, most of that volcanic activity was concentrated over a region called Imbrium, where typical thickness of the basalt is 5 kilometers. So yes, a 5-kilometer thick layer produced by volcanic eruptions. This incredibly thick layer is spread out over a surface area of about 1 million kilometers square. So while Imbrium is the second largest mare surface-wise, it has by far the greatest volume of basalt at 5 million kilometers cubic. Being on Imbrium 3.5 billion years ago would reveal a surface that from the ground is dark and solid. The atmospheric pressure would potentially be the highest at this location because this is where most of the Moon at the time got its atmosphere from. Apollo 15 landed on the rim of Imbrium Mare. The photos from the landing clearly show a surface coated in fine-grained soil. That layer of fine material on top of Imbrium is called regolith. Regolith wasn't present 3.5 billion years ago on top of Imbrium. However, currently, regolith covers the majority of the surface of the Moon. There are very few places with just exposed bedrock. Those few are at the rims of craters, and some relatively fresh craters such as Tycho, which is 85 kilometers across and is about 108 million years old. Yes, that is relatively new. 3.5 billion years ago, the surface of the Moon was also largely covered with regolith. Obviously, the large mares, such as Imbrium, had fully solid basalt ground, but outside of that, there was still a layer of regolith. However, the lunar highlands had a regolith layer that was more thin compared to today. Exactly how much thinner it was back then is really hard to say, given that the thickness of a regolith layer does not tell us that well as to how old a surface is. So the production rate of regolith is hard to determine, and therefore so is the regolith thickness 3.5 billion years ago. Still, since the layer was at least to a degree thinner, the lunar highlands back then were sharper and more rugged. They were also less weathered. They had a greater amount of exposed bedrock and were overall significantly brighter compared to mares. Over time, as the impacts scattered the dark grains from the basalt areas, the highlands took on different shades of gray. However, 3.5 billion years ago, they were a lot more white. Meanwhile, the mares were a lot darker than they are today. The fresh basalt areas were very dark, so the contrast between the mares and the highlands was much more pronounced compared to today. Most of the Apollo missions registered the regolith thickness as being about 5 meters, but most of those were in mares where the regolith is thinner, while the one Apollo mission in the highlands registered a thickness of 12 meters. Since most of the impacts already occurred by that point, 3.5 billion years ago, the regolith layer, along with the atmosphere, could have caused for dust storms to form. Near mares, so near volcanic sources, powerful winds could have been produced, powerful enough such that large local or maybe even global dust storms formed. To get some perspective on just how powerful the eruptions were, it is estimated that on the moon 3.5 billion years ago, every second about 10,000 kilograms of gas was released. So strong winds and with that dust storms were possible. With regards to looking up at the sky, such an atmosphere should technically be able to support some clouds, but whether it had any is hard to say. From the moon, Earth would also clearly be visible, but at that point, it would look like a different planet, with a nearly entirely global dark green ocean and almost no visible land. From Earth, the slightly larger moon would maybe have glowing lava visible, but it's hard to say as, even despite the intense eruption rate, lava cools down pretty quickly. Whatever the case is, large dark areas that contrast heavily to the bright surrounding highlands would clearly be visible. This image shows the timeline of when certain basalt areas formed on the moon. Clearly, the largest areas in terms of surface area formed between 3.9 and 3 billion years ago. Particularly 3.5 billion years ago is when most of the basalt started quickly filling in Imbrium mare. The moon's atmosphere likely dissipated over the course of about 70 million years. At least, that's one reasonable estimate. It could have dissipated much slower, as the atmospheric loss could have slowed down as the pressure got lower. Today, the moon still technically has an atmosphere, as in an extremely thin layer of gas near the surface. It is so thin that it isn't even visible. Besides thermal and chemical processes that affect the upper layer of the moon's surface, which then cause for the gas to be released, there are also constant small impacts that, through impact-generated vapor and melted material, cause for the gas to be released, which then contributes to the extremely thin atmosphere. Small and large impacts also contributed to the formation of the fine-grained soil that coats the moon's surface. The Apollo astronauts placed seismometers on the moon to measure moonquakes, and they did register their existence. The moon experiences moonquakes that can go up to 5.5 on Richter scale and last for over 10 minutes. This level is powerful enough to even do some damage to some buildings on Earth. And on top of that, on Earth, a 5.5 magnitude earthquake typically lasts only about 15 seconds or so, not 10 minutes like on the moon. These moonquakes originate from some 20 to 30 kilometers below the surface and are caused by the moon losing heat, which causes for it to shrink, which then creates a moonquake. There are also other causes. Some moonquakes originate from much deeper places, hundreds of kilometers deep. Those are caused by the Earth's gravity tugging on the moon. There are also moonquakes caused by meteorite impacts. 3.5 billion years ago, the moon was losing heat much more rapidly, the meteorite impacts were much more common, and since the moon was closer to Earth, the tidal forces were also stronger, and on top of that, there was intense volcanic activity. All of those factors led to the moon experiencing much stronger and more frequent moonquakes. There are thrust faults on the moon that are created due to moonquakes. A 5.5 magnitude moonquake would likely feel very scary to a person standing on the moon. There is a good chance that one could lose their balance. The lower gravity does make the falls to the ground less impactful, but it also makes retaining balance harder. Still, although scary, a 5.5 magnitude moonquake would likely not be deadly. 3.5 billion years ago, however, this magnitude was likely way more common, and on top of that, there were the occasional ones which were powerful enough to be deadly. Although not certain, there is some evidence that the Moon experienced periods in the range of thousands of years where its magnetic field reached intensities similar or even slightly greater than the Earth's current magnetic field. There are rocks that captured that level of magnetic field intensity on the Moon, but again, the Moon's magnetic field wasn't consistently this strong back then, and over time it weakened to the point where today there is a very weak magnetic field that is crustal in origin, so it varies quite a bit between different areas on the Moon. The transient but strong magnetic field that the Moon had 3.5 billion years ago also significantly shielded the Moon from radiation, so it was at least somewhat safer to a degree in one aspect compared to today. So that is what the Moon was like 3.5 billion years ago. There are clearly some notable differences between then and now, but nothing that made the Moon look completely unrecognizable. It was overall quite similar, but a lot more lively.